Section: Introduction. In this section, we discuss the importance of stochastic optimization algorithms, particularly stochastic gradient descent, (SGD), in deep learning. We note that adaptive gradient methods like Adam are commonly used, but they have theoretical convergence issues. For instance, Adam can fail to find the correct solution in certain scenarios, such as when the objective function leads it to converge to an incorrect value, especially if the hyperparameter beta-2 is small. We acknowledge that there have been attempts to address Adam's non-convergence, such as AMS-GRAD, which modifies Adam to ensure convergence in online convex optimization. However, AMS-GRAD's convergence relies on the assumption that gradient noise is uniformly bounded, a condition that is often not met in practice. We also analyze Adam's non-convergence by looking at the relationship between the current gradient and the second moment estimate. We find that excluding recent gradients from this estimate can help resolve the issue. Based on this analysis, we introduce a dA shift, but its convergence for general non-convex problems remains uncertain. Recent studies suggest that Adam can converge if beta-2 is chosen based on the specific problem, but this tuning can be cumbersome. Therefore, we aim to develop algorithms that guarantee convergence without depending on beta-2 or strong assumptions like bounded noise. To create our algorithm, we first explore the case without momentum, focusing on Armstrop's convergence for smooth non-convex problems. We identify that the correlation between the second moment estimate and the current gradient is a key factor in non-convergence. By excluding the current gradient from the second moment estimate, we can eliminate this correlation. We then extend our findings to include momentum, as seen in Adam, and discover that this momentum also contributes to non-convergence. To tackle this, we suggest altering the order of momentum updates and normalization by the second moment estimate. This adjustment allows us to resolve the non-convergence issue without relying on specific hyperparameter choices or the bounded noise assumption. We present our algorithm, named ADOPT, which theoretically achieves convergence at an optimal rate for smooth non-convex optimization. In our experiments, we first test ADOPT in a scenario where Adam typically struggles due to beta-2 choices. Our results show that ADOPT converges quickly, while Adam fails and AMS-GRAD converges very slowly. Next, we evaluate ADOPT on a multi-layer perceptron for the MNIST classification task, finding that it outperforms existing adaptive gradient methods, including Adam, AMS-GRAD, and ADA shift. Finally, we assess ADOPT in various practical applications, such as image classification on CIFAR10 and ImageNet, training deep generative models, fine-tuning language models, and deep reinforcement learning. Our empirical results indicate that ADOPT consistently outperforms existing algorithms in these applications. Section Summary. In this section, we discuss the limitations of the Adam optimizer, particularly its non-convergence issues, and introduce our new algorithm, ADOPT, which addresses these problems without relying on specific hyperparameter choices or strong assumptions. Our theoretical analysis and experimental results show that ADOPT converges effectively in various non-convex optimization scenarios, outperforming existing adaptive gradient methods like Adam and AMS-GRAD. Section: Preliminary. In this section, we define our problem, which involves minimizing the objective function, denoted as f, that maps from a d-dimensional space to real numbers, with respect to the parameter theta also in d dimensions. We focus on first-order stochastic optimization methods, where we only have access to the stochastic gradient, g. Since f can be non-convex, our aim is to find a stationary point where the gradient of f with respect to theta equals 0. To analyze the convergence of stochastic optimization algorithms, we rely on several common assumptions. First, we assume that the objective function f is lower bounded, meaning it does not go below a certain value for all theta. Second, we consider the stochastic gradient g_t to be an unbiased estimator of the gradient of f at the previous parameter value, ensuring that the expected value of g_t equals the true gradient. Third, we require that f is L-smooth, which means there is a constant L such that the difference between the gradients at any 2 points is controlled by L times the distance between those points. We also assume that the variance of the stochastic gradient is uniformly bounded, indicating that there is a constant sigma such that the expected squared difference between g_t and the true gradient is limited. For analyzing adaptive gradient methods like Adam and Ada grad, we adopt a slightly stronger assumption that the stochastic gradient has a finite second moment, meaning there is a constant g such that the expected squared norm of g_t is bounded. Additionally, for AMS grad, we assume that the stochastic gradient is uniformly upper bounded, meaning there is a constant g such that the norm of g_t does not exceed g. This assumption also implies that the noise in the gradient is bounded. In our analysis, we derive an upper bound for the expected fourth power of the norm of the gradient at the TTH step to investigate the convergence rate of the stochastic optimization algorithms, a common approach in the literature. Next, we review the convergence of standard stochastic gradient descent, SGD, which has been extensively studied. For smooth non-convex functions, it has been shown that SGD with a constant learning rate converges at a rate proportional to 1 over the square root of t, where t is the total number of updates. This rate is considered optimal up to a constant factor. For diminishing learning rates, a well-known convergence bound is logarithmic in t divided by the square root of t. While standard SGD remains popular, adaptive gradient methods are more commonly used, especially in deep learning. In these methods, we update the parameter theta using a second moment estimate, v_t, along with a small positive constant epsilon. In Ada grad, v_t is initialized to 0 and updated by adding the outer product of g_t with itself. RMS prop modifies this by using an exponential moving average instead of a simple sum. Adam combines momentum with the second moment estimate to speed up convergence. However, RMS prop and Adam do not guarantee convergence even in simple convex problems. Ada grad with a constant learning rate is known to converge under certain assumptions. Although the convergence of Adam can be ensured by carefully choosing beta_2, determining the right value for each problem beforehand is challenging. To address the convergence issues with Adam, some researchers have proposed variants like AMS grad, which modifies the second moment estimate to ensure it is non-decreasing. AMS grad has been shown to converge under certain conditions for non-convex settings, but its results depend on assumptions that may not hold in practice, particularly in cases like variational autoencoders where unbounded noise is present. Other approaches, such as ADA shift, attempt to resolve Adam's non-convergence by using past second moment estimates and calculating momentum from recent gradients. While these methods provide theoretical insights for convex problems, they lack convergence guarantees for non-convex cases. We provide a more detailed discussion of existing analyses in the appendix. Section Summary. In this section, we define the problem of minimizing a non-convex objective function using first-order stochastic optimization methods, focusing on the convergence behavior under various assumptions about the stochastic gradient and the objective function. We also review existing stochastic optimization algorithms, highlighting the convergence properties of methods like SGD, Ada grad, RMS prop, and Adam, while noting the challenges and limitations associated with their convergence guarantees in non-convex settings. Section. Analysis. Cause of non-convergence of Adam and how to fix it. In this section, we analyze why Adam may not converge and explore how to resolve this issue, aiming to create an algorithm that can converge regardless of the value of beta_2. We begin by examining a simple scenario without momentum, then extend our analysis to include momentum and propose a solution for Adam's convergence problem. First, we look at RMS prop, which represents Adam's no momentum case when we ignore bias correction. We establish a convergence bound for RMS prop under certain assumptions, where we use a constant learning rate. We define specific constants related to the problem, and we note that RMS prop converges to a limited area around a stationary point, influenced by the hyperparameter beta_2 and other problem-specific factors. To ensure this bounded area is small, we need to choose beta_2 carefully based on the problem at hand. We find that as beta_2 approaches 1, the size of this area decreases, which aligns with practical experiences. However, determining how close to 1 we should set beta_2 depends on factors that we cannot predict beforehand. We also observe that the constant term in our convergence bound arises from the relationship between the gradients and the second moment estimate. By ensuring that the second moment estimate is conditionally independent of the current gradient, we can eliminate this constant term from our bound. A straightforward way to achieve this independence is to use the previous second moment estimate instead of the current one, similar to the ADA shift method. In summary, we propose that by modifying the second moment estimate, we can improve the convergence behavior of RMS prop and, by extension, Adam. Section Summary. In this section, we analyze the non-convergence of the Adam optimizer and propose a solution by first examining RMS prop without momentum, revealing that its convergence is limited by the choice of the hyperparameter beta_2. We suggest that to improve convergence, beta_2 should be set close to 1, and we introduce a method to achieve conditional independence in the second moment estimate, which aligns with the ADA shift approach. Section: Case with momentum. In this section, we discuss the case involving momentum. We have noted that RMS prop can be adjusted for convergence by excluding the current gradient from the second moment estimate. However, when we integrate adaptive gradient methods with momentum, like Adam, the convergence analysis becomes more complex. Specifically, applying Adam-style momentum generally leads to non-convergence, even when using the previous second moment estimate. This issue arises because the momentum incorporates all past gradients, which creates a correlation with the second moment estimate. To address this, we introduce ADA shift, which calculates momentum using only the most recent gradients. This ensures that the momentum and the second moment estimate are conditionally independent, allowing for convergence. However, this method requires a careful choice of how many past gradients to consider. A small number means the momentum lacks historical information, while a large number restricts the second moment estimate to outdated gradient data. To eliminate this trade-off, we propose a new momentum formulation. The key difference from the Adam-style momentum is the order of updating the momentum and the normalization process. In our approach, we normalize the current gradient before updating the momentum, which guarantees convergence since the second moment estimate is only used for normalization. We then introduce our new adaptive gradient method called ADOPT, which stands for Adaptive Gradient Method with the Optimal Convergence Rate. We summarize the procedure in an algorithm, noting that we place the momentum update after the parameter update for simplicity, although it is equivalent to our previous equations. We find that substituting a specific normalization contributes to better performance in practice. ADOPT achieves optimal convergence rates for smooth non-convex optimization. Under certain assumptions, we establish that with a constant learning rate, ADOPT converges effectively. We also provide convergence bounds for diminishing learning rates, which are more applicable in real scenarios. In our experiments, we first validate ADOPT with a simple example where Adam fails to converge, confirming our theoretical insights through numerical simulations. We then train a multi-layer perceptron on the MNIST dataset to assess ADOPT's effectiveness in non-convex optimization. Finally, we evaluate ADOPT across various practical applications, including image classification, natural language processing, generative modeling, and deep reinforcement learning, with detailed settings provided in the appendix. For the toy problem, we consider a convex optimization scenario with a specific objective function. We access stochastic objectives and analyze the impact of gradient noise on convergence. We compare the robustness of Adam, AMS grad, and ADOPT under different hyperparameter settings, observing that ADOPT consistently converges faster, especially in high noise conditions. In our MNIST classification experiments, we train nonlinear neural networks and find that ADOPT outperforms existing optimization algorithms in terms of convergence speed and final performance. We also conduct image classification experiments using real datasets, where ADOPT shows faster convergence than Adam. For generative modeling, We train NVAE on MNIST using ADOPT and find improved likelihood results compared to the baseline. In pre-training large language models, we observe that ADOPT maintains stable training even with smaller batch sizes, while Adam struggles with loss spikes and convergence issues. Finally, we fine-tune a pre-trained language model and compare the performance of ADOPT against Adam, finding that ADOPT yields better results. We summarize additional experimental results and settings in the appendix, demonstrating ADOPT's advantages in various contexts.